Now come to wave-particle duality. According to de Broglie, electron can behave as a particle, so we can write E equal to mc square, and electron can behave as well as wave, so we can write E equal to h nu. Combining the equation 1 and 2, we have mc square equal to h nu, or mc equal to h by lambda, or lambda equal to h by mc. M is mass, c is velocity of light, so m into c is p, that is momentum. Verification of the equation lambda equal to h by p has been obtained by Davison-Germer's experiment in 1927. See this picture. Electron can move around nucleus like a wave as well as particle. The circumference of electron orbit from n equal to 1 to n equal to 4 shown in the figures. That is, electron behave like a stationary wave only. For stationary wave, circumference 2 pi r equal to n lambda. We know that lambda equal to h by mc from de Broglie's equation. Putting 2 pi r equal to n lambda, we have 2 pi r by n equal to h by mc, or mcr equal to nh by 2 pi. That is the first postulate of Bohr's theory. The Austrian physicist Schrödinger gave his wave equation in 1927. The wave motion of a vibrating string can be described by the equation psi equal to a sine 2 pi x by lambda. On differentiation with respect to x, that is considering the wave is propagating only with respect to x-axis, that is, wave is one dimensional only, we have the equation d psi by dx equal to a cos 2 pi x by lambda into 2 pi by lambda. That is equation number 2. Differentiating again with respect to x, that is double differentiating, we have d2 psi by dx square equal to minus 4 pi square by lambda square a sine 2 pi x by lambda. A sine 2 pi x by lambda equal to psi, so the equation can be written as d2 psi by dx square equal to minus 4 pi square psi by lambda square, that is equation 3. From de Broglie's equation, we have lambda square equal to a square by m square c square, or d2 psi by dx square equal to minus 4 pi square m square c square psi by a square, or d2 psi by dx square equal to minus 8 pi square m ek, that is kinetic energy psi by a square, or d2 psi by dx square equal to minus 8 pi square m. Kinetic energy means total energy minus potential energy, so Ek can be replaced by E minus Ep into psi by a square. That is equation 4. If the motion is described by 3 space coordinate, that is x, y, z, then the above equation becomes d2 psi by dx square plus d2 psi by dy square plus d2 psi by dz square equal to minus 8 pi square m E minus Ep psi, where psi have 3 coordinates x, y, z by a square, or del square psi, that is the mathematical equation written within bracket is denoted by del square, that is del square psi equal to minus 8 pi square m E minus EP psi by A squared. That is equation 5. Del square is called Laplacian operator. Or the equation can be rearranged as minus A square by 8 pi square m d2 by dx square plus d2 by dy square plus d2 by dz square. Or the equation can be rearranged as minus A square by 8 pi square m d2 by dx square plus d2 by dy square plus d2 by dz square plus EP psi equal to E psi. The mathematical expression within third bracket can be denoted by capital H, and H is called Hamiltonian operator, and the wave equation is written in the form as H psi equal to E psi, where E denotes the energy of wave function psi. In polar coordinate, x can be replaced by r sin theta cos phi, y equal to r sin theta sin phi, z equal to r cos theta. And this is the figure. R is the radial part, radial coordinate, theta and phi are the angles. So in polar coordinate, the equation may be written as 1 by r square d dr of r square d psi dr plus 1 by sin theta into d theta of sin theta d psi by d phi plus 1 sin square theta into d2 psi by d phi square plus 8 pi square m by a square e plus e square by r psi equal to 0. What is small e square by r? Small e square by r is the potential energy, and EP can be replaced by minus e square by r. That is EP equal to minus small e square by r for hydrogen atom. So the polar coordinate Schrodinger wave equation for hydrogen can be written in this form. For other mononuclear systems, E minus EP should be written. Eigenvalue equation. Mathematical operator into function equal to constant into function. Such type of mathematical equation or differential equation having the format operator into function equal to a constant into function is called eigenvalue equation. The conditions for a function to be eigen function are: the function must be finite, the function must be single valued, function must be continuous, function must be normalized, function must be orthogonal. A mathematical equation having format operator into function equal to constant into function are called eigenvalue equation, and the function which satisfied such equation are called eigen functions, and eigen functions have 5 conditions or 5 properties. Those are: eigen functions must be finite, eigen functions must be single valued, eigen functions must be continuous, eigen functions must be normalized, eigen functions must be orthogonal. In polar coordinate, psi E can be written as r of r, theta of theta, phi of phi. The angular part of the wave function may be written as capital A equal to x to the power a, y to the power b, z to the power c by r to the power l, where L equal to a plus b plus c. Psi versus r plots for 2p and 3p orbitals are represented here. Such psi versus r plots have no significance, but psi square versus r square plot are important. Psi square when increases, r square decreases. That is, when psi square decreases, 4 pi r square increases. That means when you go apart from nucleus, probability of finding electron decreases. That is, with the increase in the value of r or r square, psi square, which denotes the probability of finding electron, decreases. I repeat, when you are moving from nucleus to outward, probability of finding electron must decrease. That is, with the distance from nucleus, that is, increase in the value of r, that is, increase in the value of r square also, psi square, that is, which denotes the probability of finding electron, decreases. So as a result, r square into psi square value must be like the orange curve. It will reach a maximum value and then it will decrease. And the maxima value from the nucleus can be denoted as the surface of the orbital, where the probability of finding electron is maximum. And such plots are called radial probability distribution plots. That is 4 pi r square psi square dr versus r plot. These are the plots for different orbitals. In the first row, for 1s, 2s, 3s orbitals, 4 pi r square psi square versus r plots are, that is radial probability distribution plots are denoted here. In the second row, 2p, 3p, 4p orbitals are there. In the third row, 3d, 4d, 5d are there. In the fourth row, 4f, 5f and 6f orbitals probability distributions are denoted here. For d orbitals, you will see the probability density increases somehow at a distance from the nucleus. That means penetration power of d orbitals is less than s or p orbitals. Rather, electron density or the value 4 pi r square psi square dr is high relatively near nucleus for s orbitals. That means s orbitals have more penetration power to nucleus. With the increase in the value of r or r square, psi square, which denotes the probability of finding electron, decreases. I repeat, when you are moving from nucleus to outward, probability of finding electron must decrease. That is, with the distance from nucleus, that is, increase in the value of r, that is, increase in the value of r square also, psi square, that is, which denotes the probability of finding electron, decreases. So as a result, r square into psi square value must be like the orange curve. It will reach a maximum value and then it will decrease. And the maxima value from the nucleus can be denoted as the surface of the orbital, where the probability of finding electron is maximum. And such plots are called radial probability distribution plots. That is 4 pi r square psi square dr versus r plot. these are the plots for different orbitals. In the first row, for 1s, 2s, 3s orbitals, 4 pi r square psi square versus r plots are, that is radial probability distribution plots are denoted here. In the second row, 2p, 3p, 4p orbitals are there. In the third row, 3d, 4d, 5d are there. In the fourth row, 4f, 5f and 6f orbitals probability distributions are denoted here. For d orbitals, you will see the probability density increases somehow at a distance from the nucleus. That means penetration power of d orbitals is less than s or p orbitals. Rather, electron density or the value 4 pi r square psi squared dr is high relatively near nucleus for s orbitals. That means s orbitals have more penetration power to nucleus. Now come to probability density mapping. That means probability of finding electron when you are moving from nucleus to outside. This figure shows the probability density distribution mapping. This is for 1s orbital. This is for 2s orbital. For 2p orbital. For 3s orbital. For 3p orbital. Now come to the shape of s orbital. This is the shape of s orbital. Now come to the shape of p orbitals. There are 3 p orbitals. One is oriented around along x-axis, one along y-axis and one along z-axis. Now come to the shape of d orbitals. There are 5 d orbitals. These are the f orbitals. Heisenberg's uncertainty principle. The principle states that it is impossible to determine exactly both the position and momentum or velocity of an electron or any other moving particle at the same time. If del x equal to the uncertainties in the measurement of position and del p equal to uncertainties in the measurement of momentum, then del x into del p must be greater than or equal with h by 4 pi. Now, del x into del p equal to or greater than h by 4 pi, or del p may be divided as m into del v, that is del x into m into del v greater than equal to h by 4 pi, or del x divided by del t, m into del v into del t greater than equal to h by 4 pi, or del v m del v del t greater than equal to h by 4 pi, or m del v square into del t greater than equal to h by 4 pi equal to del capital E into del t greater than equal to h by 4 pi. That means uncertainty in energy into multiplied by uncertainty in time greater than equal with h by 4 pi. Quantum numbers of fourth type: principal quantum number represented by small n, azimuthal quantum number small l, magnetic quantum number small m, spin quantum number small s. And principal quantum number n can have values 1, 2, 3, 4, 5, 6, etc. Principal quantum number represents shells. Azimuthal quantum number small l can have n values. Those are 0, 1, 2, 3, 4. to n minus up to n minus 1. L represents subshell. Magnetic quantum number small m is equal with L into cos theta. When L equal to 0, then for any value of theta m equal to 0. When L equal to 1, then for theta equal to 0 degree, m equal to 1 cos 0 degree, that is 1. For theta 90 degree, m equal to L cos 90 degree equal to 0. For theta 180 degree, m equal to 1 cos 180 degree, that equal to minus 1. That means magnetic quantum number is orbital angular momentum component of is the component of orbital angular momentum vector small l. Spin quantum number S. Spin quantum number denotes spin of electron. Electrons can rotate around its own axis. The motion may be clockwise, then spin quantum number is plus up, or the motion may be anti-clockwise, that is, then spin quantum number is minus up. Now come to Above principle. The term Above means building up, that is, building up principle. The principle states that the atoms are built up by successive addition of protons and neutrons to the nucleus and corresponding electrons to the extranuclear part. Each added electron occupies the available atomic orbitals of lowest energy. That is, 1s orbital is filled up first, then 2s orbital, then 2p, then 3s orbital, then 3p, then 4s orbital, then 3d, followed by the 4p, 5s, etc. and so on. One s is filled up first, then 2s, fourth electron goes to the 2s, fifth electron to 2p, sixth electron in the 2p. Now the question is, why 4s orbital will fill up by the electrons and then 3d orbital? The answer is, orbital energies increases as n plus L value increases. For 4s orbital, the n value is 4 and L value is 0. That is, n plus L value is 4 plus 0 equal to 4. And for 3d orbital, the value is 3 plus 2. That is, n value is 3, L value is 2. That is, 3 plus 2 equal to 5. Orbitals having same energy are called degenerated orbitals. As example, 2px, 2py and 2pz orbitals are degenerated orbitals. Now come to the Ohm's rule. The first rule of Ohm's, that is rule of spin multiplicity, states that when degenerated orbitals are available, electrons will fill up those orbitals singly fast with parallel spin to have maximum spin multiplicity, that is maximum stability. Just like consider a double-decker bus. When people fill up the first floor seats of a double-decker bus, the single seat or window seats are occupied first, then coupling takes place. Spin multiplicity Sm is represented by Sm equal to 2 into capital S plus 1 equal to small n plus 1. Capital S is the total spin, small n equal to number of unpaired electrons in same spin. Consider the case of P2 or P3, you will find the spin multiplicity. Wolf Ernest Pauli, a student of Niels Bohr, stated that no two electrons in an atom can have all four quantum numbers the same. At least one quantum number should differ, and this is called Pauli's exclusion principle.